All right, welcome to the explainer. Every single time you send an email, buy something online, or just browse the web, there's this secret world of codes and keys working overtime just to keep you safe. So today, we're going to pull back the curtain and demystify the essential language of that world, the language of digital security.
So how does it all work? How do your secrets actually stay secret online? Well, to figure that out, let's follow the journey of one single secret message. We're going to see how it goes from a simple thought you have into this super secure piece of data and then all the way back again.
Okay, so let's start with the journey of that secret message. Any protected info, whether it's a DM to a friend or your credit card number, it follows this really fundamental path. And once you get this path, you basically get the foundation of all modern cryptography. It's that important. So here it is, the whole journey in 5 steps. Every single secure message goes through this transformation. It starts as what we call plaintext, just normal, readable stuff. Then it gets scrambled, turning into a secret code. Then, on the other end, it gets unscrambled. And boom, it's readable again. But here's the kicker, only for the person it was meant for. So let's break down each of these steps one by one.
All right, first step, plain text. This is just the message. It's your starting point and its most natural and honestly most vulnerable state. Think of it as a, hey, what's up? You type into a chat, or the password you're about to enter. Before any magic happens, it's totally out in the open, clear as day to anyone who might be snooping. So, to protect that vulnerable plain text, we use encryption. This is the first big step. The best way to think about it, it's like taking your message, putting it in a digital safe, and slamming the door shut. It's the actual process of turning that readable info into a totally scrambled, secure format. But how does that scrambling actually happen? What's the secret sauce? Well, that's where this cipher comes in. A cipher is basically the algorithm, the specific set of rules. You can even think of it as the mathematical recipe that does the scrambling and unscrambling. So if encryption is the safe, the cipher, that's the unique, complex design of the lock on that safe. And what do you get after all that? You get this, ciphertext. This is your message after it's been through the cipher. To you and me, it looks like total gibberish, just a random jumble of characters. And that's the point. This is the scrambled, unreadable text that is safe to send flying across the internet. Okay, so the message has arrived safely, but it's still gibberish. To make it useful again, it has to be read, right? And that's where the final step, decryption, comes in. This is literally the process of unlocking that digital safe, turning the scrambled ciphertext all the way back into the original readable plain text. The journey is complete. So we've talked about safes and locks, but we've missed the single most important part of the whole thing, the key. Without the right key, that ciphertext is just random noise forever. And believe me, when we start talking about keys in cryptography, this is where things get really cool. So what is a key? A cryptographic key is just a piece of info. Could be a number, a word, a whole phrase that basically tells the cipher what to do. It's the secret ingredient that makes your encryption unique. Think about it. Even if a thief knows the brand of lock on your safe, they still can't open it with a specific physical key. It's the same idea here. Now, it turns out there are 2 main ways to handle keys. On one side, you've got what's called symmetric. This is pretty simple. You use the exact same key to both lock and unlock the message. It's super fast, but you've got a big problem. How do you securely share that one secret key with someone else? On the other side, we have asymmetric encryption, which is just brilliant. It solves the sharing problem by using a pair of keys. There's a public key you can give to anyone, they use it to lock messages and send them to you. But then there's a private key that only you have, and it's the only thing that can unlock those messages. A real game changer.
Okay, so secrecy is covered, but modern security is about way more than just hiding things. Think about it. How do you know the message you just got is the exact one that was sent? What if someone messed with it on the way? We also need to be able to guarantee trust and, really importantly, integrity.
And that's where something called a cryptographic hash function comes into play. The easiest way to think of this is like a unique digital fingerprint for your data. It's amazing. You can take any message, a single word or an entire book, run it through the special algorithm, and it spits out a short, fixed-length string of characters. We call that the hash. And the most important part? It's a one-way street. You can't ever turn that fingerprint back into the original message. No way. Just look at this. It shows you the power of a hash perfectly. So the sentence,
The quick brown fox jumps over the lazy dog, creates this specific hash value you see here. But now, what if we changed just one tiny thing? Let's change fox to box. Look at the new hash. It's completely different, totally unrecognizable. This incredible sensitivity to change is exactly what makes hashes so powerful for checking if anything's been messed with. Okay, now let's put a couple of these ideas together. What happens when you take that digital fingerprint, the hash, and then you lock it with your private key, the one only you have? Well, you get a digital signature. It's pretty much the digital version of signing your name on a sealed envelope. It proves two critical things. First, it proves who sent it, because, hey, only you have that private key. And second, it proves the message wasn't changed, because if the receiver runs their own hash on the message, it should match the one you sent. All of this together gives us a really important property with a fancy name: non-repudiation. It sounds complicated, but it just means the digital signature is such strong proof that the sender can't turn around later and say, nope, wasn't me. It provides proof of origin, which brings real, solid accountability to our digital world.
All right, so we've got the building blocks, right? Encryption, keys, hashes, signatures. But that's all on a small scale. How does this stuff work for billions of people, securing trillions of interactions across the whole internet every single day? How do you manage all that?
Well, the answer is something called public key infrastructure, or PKI for short. Now, PKI isn't one single piece of software. It's a whole system, a huge framework of rules, roles, and procedures that are all designed to manage public keys on a global scale. It's the underlying system of trust that lets your browser securely connect to a website you've never been to before. When it's working right, you don't even know it's there. But when it fails, oh boy, millions of people can be put at risk.
And right at the heart of the PKI system are the certificate authorities, or CAs. The passport office analogy is perfect here. These are trusted organizations that act like the internet's passport office. They issue digital certificates, which are basically digital passports, that verify a website, or even a person, is actually who they say they are. They're the ultimate vouchers of identity online. But of course, that's not the end of the story, because for every genius who comes up with a way to create a secret, there's another genius trying to figure out how to break it. It is a constant, high-stakes game of cat and mouse. And this brings us to the field of cryptanalysis. This is the flip side of the coin. If cryptography is about making codes, cryptanalysis is the art and science of breaking them. It's all about poking and prodding at systems, looking for those tiny hairline cracks in a cipher that an attacker could use to slip through.
And you know, there's another fascinating approach. Sometimes the best way to keep a secret isn't to scramble it into gibberish, but to hide it in plain sight. That's steganography. Here, the goal isn't to make the message unreadable, but to hide the fact that there's a message at all, like embedding a secret text file inside a totally normal-looking cat picture. No one would even think to look for it. And all of this brings us to one final big question. Cryptography isn't a solved problem. It's a battlefield. It's an endless arms race between the lockmakers and the lockpickers. And with huge new technologies like quantum computing coming up, which could potentially shatter the codes we rely on today, it really makes you wonder. In this endless race between making and breaking codes, can our secrets ever be truly safe?